Okay, so now we know that if we've got a variable that's normally distributed and we take a random sample of that variable, sample mean is normal, centered on mu with standard error sigma on root n. That's a really useful result, and we can do all sorts of stuff using that result. But for starters, what we're going to do is we're going to think about sample size determination. So let's assume hours slept is normally distributed. We don't know the true mean, but we're going to say that the standard deviation across people is 2.5 hours. So there's a fair bit of variation there, about two and a bit hours, 2.5 hours. And we're also going to say that ideally we would like to estimate the true mean to within, say, 15 minutes of its true value. So we want the difference from the true mean to be less than a quarter, 0.25. For a sample of size 5, what's the chance of getting within a quarter of an hour of the true mean? Okay, this is a probability we want to calculate. We know x bar is normal, centered on true mean, with standard deviation sigma on root n. So sigma is what, 2.5? N is 5. So what's that equal to? All right, 1.12. So we got a normal distribution. We know it's standard deviation. We want to know what x bar minus mu is. Well, whenever the probability of something to do with x bar minus mu, whenever we've got a probability to do with a normal distribution, we can always standardize. Okay, so I'm dividing both sides by the standard deviation of x bar, 2.5 on root 5. The reason I'm doing that is because it gives me something that I know about. It gives me the standard normal distribution. And so absolute value of x bar minus mu divided by the standard error of x bar, the standard deviation of x bar, that's just the probability of, that's just the absolute value of the standard normal. Because this guy had standard error 2.5 on root 5, if I divide this expression by 2.5 on root 5, its standard deviation becomes 1. So it becomes, so if x bar is normal, x bar minus mu has mean 0, x bar minus mu over standard error is normal with mean 0, standard deviation 1. And so what's that equal to then? .223, 0.224. So I got a standard normal variable centered on 0, standard deviation is 1. I get this area here. This is the area I want to find. How am I going to use MATLAB to get that? I can use the norm CDF function. Norm CDF gives you area to the left. Okay, so I can do that. That there is norm CDF of 0.224. I want to subtract off this one. I want to subtract off that one. If I take the green area minus the orange area, that'll give me my answer. So I'm going to take the difference between those two. Why don't I call this thing here Z? I'm going to go norm CDF of Z minus norm CDF minus Z. And I get an answer, which is that was exact. 0.177. So about 17 and a bit % of the time, you would get within a quarter of an hour of the true answer if you sampled 5 people. All right, what if n equals 50? If n equals 50, I do all these same calculations. With n equals 50. So, for n equals 50, square root of 50, is 0.354. So instead of having a 1.12 on the bottom, I got like a 0.35 on the bottom. Z ends up being 0.707. Oh, there's a 50 now. It's 50 there. .71, give or take. We end up getting 0.52. So if you take a sample of 50 people, because 50 gives you more information about what the true mean is, you sample 50 people, you end up with like about a 50-50 chance of getting within a quarter of an hour of the true mean. It's better than before. Before it was like, what was it? It was like a 7% chance, something like that. So before n equals 5, there was a lot of variation in our sample mean. N equals 50, we're getting closer to the true mean. So if we want to know how often you get within a quarter of it, it's happening a lot more often at n equals 50. What if we want to get within 15 minutes of the true mean 95% of the time? Okay, so to do this one, I guess we're going to not plug in a specific value there. We're going to leave that as n. We're going to leave that as n. And we're saying that this thing here is equal to 0.95. So now it's a little bit different. It's a little bit different to this curve now, isn't it? We want to find the value so that 95% of the time we're within that far. So I'm just going to call it Z star for the moment, a special value of Z, which will come up once or twice in this course more, I tell you. Okay. We want to find the value Z so that 95% of the time we're within that many standard errors of the true mean. So I guess what I'll do is I'll use norm inv. Instead of trying to find a CDF value for a given Z, we're trying to work backwards. We want to work backwards and say, given that the area to the left is equal to some value, what's Z? So we're doing the inverse function from norm CDF, which MATLAB writes as norm inv. Now, if it's 95% in the middle, and this thing's symmetric, about 0, it's 2.5% off each end. The area to the left is going to be 97.5%. So we want to find a value Z so that 97.5% is the chance of getting less than it. Norm inv 0.975. The answer ends up being 1.96. So if this expression here is equal to 0.95, then that's equal to 0.9, if this one is here is equal to 1.96. There you go. We just solve for n now, don't we? Just solve for n. We got an expression where everything's known except for n. So I'm going to say that is, that root n, it's a divided by thing going on there. So this is like root n times 0.25 over 2.5 is equal to 1.96. So n is equal to, it's going to be 10 times 1.96. It's going to end up being 19.6 squared. So I go this times 2.5 divided by 0.25, and then I'll square that whole thing. Okay, so I mean that is 19.6. I square that. I get 384 in a bit. So what sample size is needed to ensure that we're within 15 minutes? You need more than 384.1. I would say sample 385 because that's more than 384, isn't it? And that would guarantee. So what we've been able to do here, if we can assume sleep is normally distributed, we take a random sample of sleep. If we know the standard deviation is 2.5, we can get, we're pretty confident, we're 95% sure we'll get within 15 minutes of the true value for how much sleep students get based on 385 samples. Okay, when I say the true one, mu, the true mean, I am talking about what would happen if we went to every student, every single student, asked them how much they slept last night. The true mean mu. We're able to say something with 95% confidence about the true mean. Based on, like, we're able to get within 15 minutes of the true mean, 95% with 95% probability, if we take a sample size 385. It's a pretty cool tool. We can use this anywhere to work out what sample size we need to get a certain accuracy. If we want to find, so we know that if we took sample size 5, well, it was like 7% chance of getting within 15 minutes of the true mean. 50 observations, if you average 50 observations, you've got about 50% chance of getting in within 15 minutes of the true mean. We now know that if you take about 385 observations, if you want to get within about 15 minutes, 0.25 of the true mean. Take a sample this size, you get in that range 95% of the time. Whereas before it was only, 50% or less.